introduce the magic for the other mic. It's your very first chance to run and get a drink before we start. You've got 3 minutes. All right. You need to make sure that you ask that wrong.
That's why you stay
and it's my wonderful pleasure to be here partnered up with the Institute of Physics for Physics in the Pub. I, by day, work at the AIP Communications. By night, I put on a silver cape and monster my shirt and doing gigs like this around the country. If you want to contact me, there are my deets there. You can hire me for weddings, parties, conference dinners. Look, first I'm going to throw to the Institute of Physics. I want you to practice your huge ovations for all of the speakers for tonight, because it's a remarkable occasion, right? There are physicists who have stepped out of the ivory tower. They're not used to the normal people. You know how you tell if a theoretical physicist is extroverted or not? They look at your shoes instead of their own. Anyhow, they're out here and they are going to talk to you guys, and you guys are going to have a great time. And you're going to show that in an outpouring of love, such as this that you're about to do for Till Weinhold, who is the local branch president of the Institute of Physics.
very much. Look, I just want to also call in line and say hello. Thank you very much for turning out. This is a much bigger crowd than I expected. I'm really pleased to see you guys all here. As Phil pointed out, yes, I am the chair, not president, of the Australian Institute of Physics Queensland branch. We've partnered up with Phil contacted us to put this on, and we ended up getting a National Science Week grant. So as you all know, it's National Science Week, right? So for the next 8 days, science here, beep away, and have lots and lots of fun. I'm really looking forward to tonight. I actually haven't seen any of these skits before, so I'm actually really keen to see them. And yeah, let's go and have a great time. Thank you very much for turning out.
Okay, so just a little bit of housekeeping first. For the sake of our presenters, so they know who they're talking to, because normally they can speak to other professors and then it's going to be but you guys might not be all professors, so just for the sake of it, I want you to do a little exercise. Put your hands in the air if you went to primary school. Okay, and put your hand down when we reach the level at which you discontinued your love of education. Okay, primary school. Who went to high school? Who did high school science? Who did science above year 10, year 11 and 12? Who did physics in year 11 and 12? Who did physics at university? First year, second year, third year, honours, PhD. Who's a professor? Alright. Hear that, presenters? None of this. But on the other hand, you guys out there, if they do say something really like heavy duty that you just like, I have no idea what that is, you make an appropriate noise and go, okay, so if I were to say, so we solve the multi-dimensional Schrodinger equation with unbounded boundary conditions, you would go, excellent. And if they told you a joke about the neutron that walked into the bar and the president is the one that says, for you, no charge, you go, no, you got it wrong. Ha, ha, ha. This is a difficult crowd. Okay, ready? Try that again. Should we go for what was the one I used before? That was good. Anyhow, punchline, go. Bit more, punchline. That's excellent. And if they tell you something that does actually blow your mind, you go, alright, ready? 1, 2, 3. That's pretty good. You guys clearly need another drink. Alright, you get the idea. So, also I want to just check what you guys found out about tonight. So who saw it on the National Science Week website? 1, 2, 3, that's exciting. Okay, who saw the Facebook event? Who knows somebody who's speaking? Who saw it on Twitter? Twitter's such a dud. It's all about Trump, but it's basically what else have I got? Who saw it on the Visit Brisbane website? Who got quantum thought waves from me? Did. That's weird. Okay. Who got an email about it from an email list from the Institute of Physics, for example? Yep, excellent. All right. Good. The other thing to confess is that I have no voice. There's a very strong chance I'm going to lose my voice. I'm trying not to speak loudly. I'm on honey lemon here, so there will be times during the night where you will be called upon to sing in my absence. So be ready for that. But that's all right, it'll be fun. Okay, so our first speaker for the night is going to save the planet, basically. Who did physicists save the planet? I thought they just sat in the ivory tower, but no, Craig Bowley is studying fusion energy, and he might do a live demo of 200 million degrees right here, or he might not. Either way, give him a huge round of applause.
Good evening and welcome everybody. Everybody here with tonight? Yep. Excellent. Those in the back, just say, let me know if you can't hear me. Just shout really loud that I can't hear you. Okay, good. Excellent. So, this is a physics presentation, and the first rule of physics presentations is you must start with a picture of either you, if you're talking about slow, boring things, or if you're talking about fast-moving, cool stuff, you need to start with a picture of, what's that guy? Albert Einstein, that bloke. Second rule of presentations like this, and consistent with what Phil's told me, no equations. There we have an equation. E equals mc squared. Now, I think I'm on safe ground here. I suspect most of you have heard of it, and I imagine most of you have got a pretty good idea what it means. Energy, mass, speed of light squared, sounds cool. What's it actually mean? Well, what it actually means is you can turn a little bit of mass into a very big bit of energy. Which is cool, but how? Now the big dramatic thing was when the slide changed, but it didn't, so that's good to know. Change the slide, please. There we go, excellent. Now we've moved along, good to see. So there are two ways that we do this. We have nuclear fission and we have nuclear fusion. Fusion's the bit I'm interested in, by the way. And in both of them, we get to turn mass into energy. But do we actually get to destroy any mass while we're doing it? Well, if you start with fusion, or start with fission, you start with a big atom, you make it into two smaller ones, and you count all the protons and neutrons you have beforehand, you count them all up afterwards, and they're the same number. So why are we saying we destroy mass? Same with fusion. Oh wow, that's even better. In fusion, we start with two. This is really good. This diagram is really helping my concentration. It's working out well. With fusion, we start with two really little atoms and make one still really little atom. But we've still got the same number of bits before and after. Why? Well, it turns out that the bits you had before were wiggling around and jiggling around. I can't really do that with the microphone because this sort of thing happens and my voice goes in and out. But the general concept is there. There's a lot going on inside a uranium atom. It's really busy and stuff is moving fast. When you break it up into two smaller ones, things are a bit more relaxed. This is because uranium atoms are unstable. You may have heard this before. And so what you've really done is you've taken all that internal energy, all the wriggling and jiggling, turned it into external energy. The thing starts moving really, really fast. If you're in the way, I recommend you get out of the way of it, it will hurt. But what we've done basically is taken internal energy that we can't use and turned it into external energy that we can use. We can use it to boil water. Excellent. Just like a big steam turbine. And we can get power. Fantastic. We do the same thing with fusion. Start with two little atoms, take a slightly bigger one. The slightly bigger one wants to go very, very fast and we can use that to boil water. This is a good thing. But really what we're doing is turning energy into energy. So, what can we do? We can do fission, we can make bombs. That's not such a great idea as it turns out. We can make power plants. Now, depending on your point of view, you may think that's the best thing since sliced bread, where you make things like this and say that's not so good. Fusion, we can make really, really, really big bombs. Again, this is not really a great plan. Or, we hope, we can make power. And if we can make the power, there's some really cool things about that. We'll get our fuel from effectively seawater. Hydrogen atoms, about 2% of them in seawater, make up our fuel. It doesn't matter whether the sun is shining or not, it will still work. It doesn't matter whether the wind is blowing or not, it will still work. These are good things. We don't get a big radioactive waste problem, and for the systems that we're looking at, they can't melt down. You can't have a Chernobyl fusion system. If you were standing right next to it and the thing went as badly wrong as possible, you'd go, bah! That was a lot of money. So how do we do it? Well, one way is lasers. Take a medium-sized building, fill it with lasers, and a thing about this good, and put a little tiny bit of hydrogen inside it, aim all the lasers at the little bit of hydrogen, and you get a very small amount of fusion. At the moment, you may be unsurprised to learn that it takes a lot more power to turn on those lasers than you actually get out of the fusion. People are working on this problem, they are spending a lot of time and money. Their time, someone else's money. And if they can get the lasers turned off and on faster, that'll be good. The other way is to get your little particles, your bits of hydrogen, moving really, really fast. Really fast means really hot, about 100 million degrees. That sounds really quite warm, and it is. There's no bottle on Earth that will actually contain that. There is one in the sky, it's not there at the moment. If you look at the moon, you can see its reflection, but other than that, you'll have to wait till the morning. But when you get things moving at 100 million degrees, fortunately for us, the electrons and the protons don't want to hang around together anymore. They break apart, and you have what's called a plasma. Now, plasmas, as it turns out, are actually really common. All the stars are plasmas. What's really rare is cold, dark stuff like the planet Earth or people in this room. So, plasmas are actually a pretty common thing. Now, why do I say it was lucky that the protons and the electrons separate? Because protons and electrons respond to a magnetic field. If they run into a magnetic field, they will stop and go back the other way. So scientists back in the 1950s worked out that you could use this to keep them in a bottle. They will go put some big magnets around the outside and send your ions running around on the inside really, really fast, about 100 million degrees. Eventually something will go splat and you'll get bits of fusion out and you'll get energy out, and hopefully you'll get more energy than you started with, which will be really nice. At the moment we get less energy than we started with, which is why people are spending a lot of money working on this. The other problem is that the thing tends to be unstable, which is to say that it goes out, not to say that it goes bang. But the idea is to get it to keep working for long periods of time. So the current state of the art is a thing called JET, which is the smaller one here. You see this little tiny person here. I've been to see JET, it's pretty cool, and yeah, it's sort of quite big. And they've been running that for about 20 or 30 years, and there's been a lot of very valuable research going on there. And at the moment, the new latest and greatest is a thing called ITER, which is being built in the south of France, in the French Riviera. So if you don't think physicists know how to have a good time, you're right. They go to the French Riviera and they go and do this. Now, ITER is what we are hoping will be the proof of principle that this thing works, that we can use fusion as a power source for a very long time. Now, as it happens, it actually came out of a discussion between the Russian president and the US president. Might surprise you. Particularly might surprise you to discover it was Gorbachev and Reagan. Things take time, people. This takes time. This is an international collaboration. It's costing 20 billion euros. That's to build it and then another 20 to run. So it's going to be quite expensive. But if we can get this thing to work, we have a power supply that can last us for billions of years. This is a pretty cool thing. Now, people will tell you that fusion is 50 years away and it always will be. Well, it's probably true that it is 50 years away. But hopefully, if you ask me next year, I'll tell you it's 49 years away. Thank you and good night.
Alright, fabulous stuff, Craig. Thank you very much. Our next speaker for tonight is also going to talk about large and hot, and maybe a little bit of a demo as well. He's talking about supernovae. So hopefully we'll get a supernova live on stage here, which is really hot plasma going everywhere, lots of amazing elements created, or not. But anyway, he's a PhD student at UQ. Welcome, Sam Hinton.
So you're about to hear two talks about fusion. Lucky everyone. I don't have too many jokes for this. This is more a story, and I'll launch into it as all great stories do. It starts the story that you probably heard before. A long time ago, in a galaxy far, far away, but this is a physics talk, so I put some numbers in. 12 million years ago, in the galaxy Messier 82, two orbiting stars came together to form one of the brightest fireworks in the history of the universe. A type 1a supernova. But it's easy to say but really hard to convey the sense of scale of these things. That's the case for everything in space. It's probably bigger than you think, even if you already think that it's bigger than you think. So what I'm going to try and do is show you how big it is. And there's a great analogy here. This is made by Randall Munro, creator of the XKCD series, and hopefully everyone's familiar with that. If not, Google it. And he asked the question, what would win? What would be brighter or more painful? A hydrogen bomb detonated on your eyeball, or if the sun 150 million kilometers away went supernova? Does anyone want to guess?
Supernova.
Yeah, that's what I'm talking about. Hopefully what surprises you is that the supernova is brighter by more than 1 billion times. In fact, to get them the same brightness, you need to take the sun and move it half a light year away. And that's still equal in intensity to a hydrogen bomb detonated on your eyeball. So hopefully no star near us goes supernova anytime soon, because it's really bad news for us and there's not much we can do about it. To take the weakest supernova that I can find out in nature and move it somewhere that is brighter than the full moon, I have to move it to over 650 light years away. Do you know how many stars are within 650 light years? Neither do I. There's too many of them. There's a lot. which is bad news for us in the next couple 100 million years. I mean, I won't be around for it, but hopefully someday someone will get to experience a supernova sufficiently far away. Alright, I'm going to skip the first half of this video. So I'm going to tell you how does a supernova actually form. So here you've got two orbiting bodies. The one on the left, the small but heavy one, is a white dwarf. And it's a star with a whole bunch of iron in its center, not much active fusion going on. And on the left now is a gas giant. Now the white dwarf is small and dense. Its gravitational force is huge, so it will start stripping gas from the giant, sucking it up, until it hits this limit, 1.44 solar masses. Stars, they're normally in balance. You have pressure from nuclear fusion pushing out, and gravity pulling in. That's a nice balance. That's how I like stars, very healthy. And the problem is if you keep adding mass, gravity gets stronger. When gravity gets too strong, it wins, and the star implodes. It doesn't explode, at least at first. But as gas collapses in, it's going to get hotter, it's going to get more dense. And what happens is it reaches a critical limit where it's hot and dense enough that there's a wave of fusion that rolls through the star. And that turns vast amounts of the matter left over, well, it fuses them together, releasing a bunch of energy, as you've just heard. This is not good for the star, and that's when it explodes. And it releases a huge amount of material, radioactive material, just to make it fun, into the cosmos. Which brings us to why we should actually care. This is the Tycho supernova, by the way. 400 years ago this went off. And we have like sailors' logs from the 16th century documenting this in the night sky. Right, so who cares? So anyone that likes stars? I like stars, I study them.
Anyone else like stars?
Everyone. Right, so here's supernova 1987A. You love how creative astronomers are in their numbers? Yeah. And what Hubble has done is taken an image of it every year for the past, well, since it was discovered. And you can see what's happened in the center here as supernova has gone off. Now, before it's gone off, when it started stripping the gas off its partner, some of the gas was sucked up by the star, some of it was expelled. And it was expelled in a ring-like fashion. And then you can see, years after the supernova goes off, the shock wave from the supernova explosion hits the gas that was expelled years before, and you can watch it light up. So it's just gone from gas into plasma, and the pressure wave that's hitting it can now trigger the creation of new stars. That is, once you get gas and you squeeze it a bit hard, once again, when you squeeze things, make them more dense, gravity wins, these might start collapsing and forming new stars now. So supernova actually create a lot of stars, which is fantastic because stars have planets, planets have hopefully us and other things on them.
Beer.
Yes, yeah. So here's another really interesting animation. This again, the Hubble. Every nice image you see from the night sky is pretty much the Hubble Space Telescope. And this is over the course of several years. This is an atypical nova that has gone off, and you get to watch the dust. There's about 50 images, I think, that NASA has taken, and they've stitched them all together. So this is not CGI or an artist rendition. This is a real thing, which is fantastic. Ooh. It's like a ghost light there. I'm pressing the button. Yeah. All right. Next group of people that like it, people that like planets. Now, I'm going to touch on the fusion thing again. When the Big Bang happened, we did not have planets like Earth. Big Bang gives us very specific things. Hydrogen, helium, lithium, deuterium, useless element. Everything else comes from fusion. Now, normally, you can wait, and stars will fuse hydrogen, or fuse helium, carbon, oxygen, but then they'll stop. They'll get to this iron core that I talked about earlier, and the reason is from this graph here. And it's the same reason we have fusion bombs and fission bombs. And that's the binding energy. We can think about this as the mass. You know how we said before that there's no protons or neutrons made, there's just a difference in energy. So this is a chart of that difference in energy. Notice there's a peak at iron. So you cannot fuse anything greater than iron and get energy out. You need to put energy in. So you don't get that for normal stars. To get above iron, you need a phenomenally powerful event, like a supernova. So everything above iron essentially comes from that. All the modern electronics we have with their fancy metals, everything comes from the gold in your jewelry. Fantastic. And because Earth is better than Jupiter, right? This is how we get Earth, supernova. And the final point is anyone that likes science. I'm going to skip over this a bit because people like science, but you don't want to see math. So what I've plotted here, going off in the skies, a 3,000 supernova observed by the Dark Energy Survey. Every dot on this plot is a galaxy. The colors represent different surveys. If you're curious about this, I made this last week, so you can come and talk to me about it, and I'll explain everything that's going on here. Right, so I've been through to the final point. Who likes supernova? Anyone that likes stars, planets, or science? I mean, there should only be a few people that don't like it. Please put your hand up if you fall into that circle, and then leave. Get out of it. All right, so that's me done. Hopefully you guys know a bit more about supernova now, and hopefully we don't see one in the night sky anytime soon. Thanks very much.
Right, explosions in space that actually create beer. Isn't that great? That's what a supernova is. Basically, the planet will be without it. So, anyhow, moving along to something much more practical, we have in the room an engineer. Very exciting. They are like physicists, only they can do stuff. But even that's not going to work for Neil Boucher because he's trying to make himself redundant so he doesn't have to do stuff anymore. Let me tell you all about it.
Okay, I'm going to talk about artificial intelligence and what it's going to mean to everybody. Can I have a show of hands if someone who more or less knows something about artificial intelligence? Half the people here, okay, about half the people here are going to be redundant in 5 or 10 years' time, and they know why. The other half are going to be redundant as well, and they don't know why. So, what we're going to do, we're going to go through it. You'll find that what you read on, you hear on ABC and news media or whatever, only tells part of the story. Now, this is a normal computer, and I'm starting with an i7 and a fairly high-speed one, because if you're serious about doing science, you really can't play with toy computers, and this is about the top of the cheap computers. Now, I'll go back. Yeah, and AI can be done on an i7 as well, but it can't be run on i7. So you can't really run AI at home. Okay, this is what you need to run AI. A huge, great, big, massive, ugly machine like that. And how it's done is you write your program on an i7, which most of us have on our desk. And then you upload the program, usually via the cloud, and you upload it to one of these monsters. This monster's got a memory of 160 terabytes, which if you don't know what that is huge. And you pay per minute or per second the time on that machine. And that's why you don't see AI everywhere, like the ABC implies, and the Australian and people like that. It's because you need one of these things. And this is a room size or even a house size. AI is also what makes a robot work. Now you'll see lots of different robots if you go to the science shows and the electronics trade fairs in Asia and Europe. And these things either have inside them a fairly powerful computer, or more likely have a radio link to a really decent computer somewhere in the room or out of sight. And they can do all sorts of things, but they're using artificial intelligence. Artificial intelligence is very, very different from what you get out of your normal i7 when you're doing Word or processing data. Now, quantum computer is also a huge computer. It takes up the best part of the room. This is not what we're talking about. This is not artificial intelligence. This is a toy for physicists. That's all it is. So we won't discuss that anymore. This is what artificial intelligence is. It's almost everything. And it's better at medicine diagnosis than doctors are. It's better at self-driving cars. Accident rates should go down to 5% of what it is now when they're on the road. People are not much good at anything, teaching or driving or middle management or physics or anything, or surgery. AI can do it better. At Sound ID, we do sound recognition. We need AI to do sound recognition much better and to handle very large data sets. And you just simply, we get bigger and bigger computers. Even if we use a supercomputer, there's a limit on what we can do with a supercomputer. And AI can bypass those limits somewhat. AI works by copying the human brain. And we don't know how the human brain works, but we can copy it. We more or less know what a neuron does, and we more or less know how they're interconnected. We more or less know how it fits together, but we don't really know. But we can simulate it fairly well. What you'll find is there is no such thing as AI. Now people think, oh, there's an AI and that's most of the story. It's not at all. There are almost as many AI types as there are people doing AI. And you hear all the acronyms for AI, which I haven't brought in the up of these neuron types. I'll show you some later. And there are so many acronyms that really everybody's got their own preferred way of doing things. And you just keep on trying until you get the one that works best for your project. Here's a neural network. A bunch of neural networks. This is a list of the neural networks as of quite recently, about a few years ago. And you can see it starts at the very top there, just with a few simple neurons, and it gets down to very, very complicated messes of networks here. And these are only just standard types of neural networks. There are a very, very large number of them. This is what the brain looks like, each neural network. You can see it's a really horrible mess, but it does sort of work. And we know it sort of works. So we've got 10 to the 11, that's an awful lot of neurons in a brain. We can't do that even on a supercomputer, but we can come up pretty close. That means we really can't, at this stage, simulate a human brain. But if you take into account that a supercomputer today is the desktop in 15 years' time, then we will be able to do that. And so you've got a little bit of time before you're made redundant. And until you can put the supercomputer on your desk, you won't be able to replace people yet. But it's going to happen and fairly quickly. Now, before, I'm almost running out of time, which is good. I've only got to summarise 40 years of development in 8 minutes. And, you know, this is quite easy. What we need to make an artificial intelligence machine work is deep learning. Now, that's something new. It's only been around for a couple of years now. Deep learning is what you use when you send up to a supercomputer the information from your little i7 or whatever. You let the supercomputer, which has hundreds, maybe thousands of processors, but it's really just the same as your i7 with a lot more processing power. You let it do all the working for you, so you give it the program and you get back the results. And that is all you need to know about artificial intelligence. It's going to be 5 or 10 years. You're going to be redundant. Most people will be redundant within 10 to 20 years. It depends on really how long it takes to get the supercomputer on the desk.
There's something to look forward to. We don't need to go to work, we can just come to physics in the pubs and have a great time. So, one thing I wanted to do, sometimes science doesn't always go quite as fast as you kind of hope it would. And one of those things was the Pluto flypast in 2015. And so I'd like to talk about that now, even though it's 2 years later. But the reason I want to do that is because the link to the New Horizons probe that was sending the data back has taken 18 months or so to get all the data from Pluto back. So I'm going to give you a bit of an update on Pluto. Who loves Pluto? Who thinks Pluto was a bit sort of hard done by? Oh, who's still got a chip on the ears? Deeply emotional argument this one. But anyhow, let's just talk about it. So there's this tiny little probe. I was lucky enough to be American. I saw the replica of it and sort of hanging from the roof in the Air and Space Museum in Washington. And it, you know, it's about from that cluster of lights to this cluster of lights in size, and it's gone 6 billion kilometres to Pluto. It's quite an extraordinary achievement of the human race. And this is what they saw. Prior to this, we just had these splodgy lump photographs from the Hubble telescope, and we didn't really know what Pluto would look like, but it's really quite fascinating. For a start, it's got this thing, this large icy plain called the Tomball Plain, and a lot of people saw things in that. For example, Pluto loves us. That's not what was actually there. There are some things. It actually was Pluto. Once you've seen it, you can't unsee it. It's still there. Anyway, up close, Pluto is quite amazing. There are these mountains on here. On Earth, when water freezes, it turns into glaciers and it flows. But on the surface of Pluto, at minus 200 something degrees,
Water freezes so solid that it's like rock, and it actually builds up these mountains. So the mountains are made of water ice. Instead, you get nitrogen, which is liquid down to minus 196 degrees, and then becomes solid below, minus 200 and something. Mixtures with methane, they're the forming glaciers. And with this false colour that, basically some infrared and ultraviolet images all combined, you can see there's a really lot of variety on the surface of Pluto. It's not like our moon, which is kind of, a bit of a boiling lump. Pluto is quite fascinating. So here we're going to do a little flyover of the... I should play some music for this, shouldn't I? What's interesting, if the surface was very old, it would be hit by a lot of asteroids and there'd be craters everywhere, but the craters are very sparse. So what that tells us is that surface is actually quite new. So Pluto, like our Earth, which through geological activity, through the movement of the tectonic plates, is refreshing its surface, Pluto also has a way of refreshing its surface. And then we come onto that tomball plane. You can see it's got these funny little sort of honeycomb structures on it. It's quite an amazing thing. I don't know about you, but it gives me chills to be flying over Pluto. It's so far away and it's been so remote for so long. One of the amazing ideas they had was that after New Horizons went past Pluto, they turned around and took a shot backwards so that they could see the sun illuminating its atmosphere. And that gave them an idea of how big its atmosphere was. And you can see there's actually quite a lot of gas. And it kind of doesn't make sense because there seems to be more gas coming off of Pluto than was possible over the 4 billion years of the solar system's life. It should have evaporated into nothingness. So there's sort of something going on. Pluto itself actually doesn't rotate in the normal plane. Like the Earth is off to 23 degrees, Pluto's almost at right angles. So what it does, part of it is in summer for 124 years, and then it rotates around and has winter for 124 years. How about that? I come from Canberra. And so clearly there's a lot of gas, when the North Pole is facing the sun, it's getting all of the sunlight, it's very weak sunlight, but it's all the time, and that, evaporates the gas, or sublimes the gas would be the technical term. I can see, yeah, thank you. I knew you would pick me up. And then it deposits somewhere else, and that's how the surface is getting renewed. But we really don't understand it. So anyone who's looking for a PhD topic, that's a beauty. Also, its moon, Charon or Charon, depending on your political persuasion, has a very interesting surface. For example, this very large feature up here, which has been nicknamed the castle. But anyhow, back to the original question that you all really care about. Should Pluto be promoted? Who thinks it should be put back as a planet? Oh, smattering. Who thinks it's just quite good where it is? Yes, okay, let me take you through it. What people who didn't... It all begins with twerking, right? What's twerking? It's with Uranus. Hello, Uranus? Right, so as Uranus was going around in its orbit, astronomers about 100 years ago realised that it wasn't going smoothly. It was slowing down, it was speeding up, slowing down, speeding up. And that was possibly because there was some other large planet there whose gravitational force was affecting Uranus. And they went and looked and they found Neptune. Great predictive science. Then they went and did the same thing because Neptune was twerking as well. And so they set a PhD student onto it, of course. And here's his photographic plate. This tiny little blob here moved from there to here. It's now a tiny little blob there. Wow. And some poor PhD student, Clyde Tombaugh, managed to discover this. Imagine the PhD hell of looking through all these plates. Anyhow, he did it January 23 and January 29, 1930. He found Pluto. extraordinary achievement. At first they thought because of Neptune's movements it must have the mass the same as the Earth. As they observed Pluto, by 1948 they'd revised that to be about 100th of the Earth's mass around Mars. Today, 1/500th. So that's kind of weird because that's having a big force on Neptune. Here's a comparison with the Earth and the Moon, and there's Pluto and Charon. They're the original Hubble images before we got up close. It's also got this very interesting orbit. It comes inside of Neptune's orbit sometimes for part of its orbit. And you can see it's also not flat like all the rest of them are. It's on this crazy angle out of the solar system. So it's looking more and more like a bit of an outlier, Pluto. When we got up close, we discovered it has 6 moons. Funny shaped things, spinning very fast. And the very interesting thing is that, it's cut off on the bottom here, but Charon is 11.6% of Pluto's mass, meaning it is heavy enough to actually make Pluto, the one in the middle here, be disturbed. So, and the centre of mass of the two bodies is actually not within Pluto, and that technically makes it a binary system. So Pluto is not a planetary planet; it's a binary system. So it's a very unusual system. Around the middle of the century, 20th century, people began to think that maybe there was a bunch of other things out there as well. A few people proposed it, there was limited evidence. Somehow it got named the Kuiper belt after Gerard Kuiper, who was not the first to do it or the most persuasive, but somehow his name stuck, so that's cool. And the proof came from Hubble in 2006 when it found this blob, which was initially named Xena, the warrior princess, by some nerds. Unfortunately, it then got revised to the classic sort of Greek mythology name, and so that's Eris. And the problem in Eris is that it's bigger than Pluto. So do we have to make Pluto a planet? And soon we discovered there were a whole lot. And the astronomical community was faced with this fairly major problem. Are we going to put all of these things in as planets or not? So in 2006 at the Astronomical Union in Prague, I've got my little test for you first. Okay, what's the most number of planets there have ever been in the solar system? Yell it out, take a guess.
9.
8, 9, more.
20.
12, more.
20.
100, too many. The answer is 23. Okay, what year? In what year were there 23?
1973.
In what year?
1948.
1948, earlier. 1937, earlier. 24, 1851 is the answer. Why? Because of the asteroids. In the middle of the 19th century, technology was at a stage where they began to pick up asteroids, these small things, and they went, oh, well, we better call Ceres planet, we better call Pallas planet. And then they went, hold on a minute, this is looking a bit silly. Because there's actually hundreds of things, thousands, millions of things in this orbit. And this is the same situation we're finding here. By luck, Tom Bohr had found something kind of in the right place where there's in fact thousands of Kuiper belt objects. And so the International Astronomical Union decided it had to set criteria for a planet. The first one, planet must orbit the sun. Okay, the moon, our moon is not a planet because it orbits the Earth. Must make itself spherical under its own gravity, must be big enough to not be one of these funny shaped things. And the last one must clear out its orbit. It must dominate the orbit as the Earth has done. All the little bits and bobs, the Earth has obliterated them, it's smashed them, kicked them out of its orbit, and it now owns the orbit. That's what Pluto needs to do to become a planet. So, I'm going to sing a little song, and I hope you'll join me. Of encouragement to Pluto. Takes a long time to put it. Here we go. We've got it. With apologies to the this is called the conclusion. Don't be annoyed, sing along. Take a swim, we can sound together. Don't be afraid. Meet your mates out to storm the air. Remember to make out your own. And we're all alone, all the rejection that you felt, take it out on top of it. Just give those tiny words the shoulder. Sure that it's just you that proves you do. A planet must be a little bit older. Hey, perhaps it's a jet. You never see how makes you look beauty. And sees the small belt. Well, she's quite built, but she's not a match. All that attached with the wall. Some say it's a bit wrong. I know he's just someone to rotate with. The entire kind of belt. God give me help. We can't have you planets by the thousand. Don't tell that you're sneaking inside his voice. Eccentric, it's hard to ignore. If we're to be sure that you're a planet. Fabulous, so the top notes there. We're going to have another honey and lemon because it's break time, and believe me, in the second half things get just a little bit crazier. So join us back here in 15 minutes, grab a drink, spend a lot of money. The Loft has been very kind to give us this venue for basically free, so get stuck in.